Welcome to PowerUP, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on PowerElectronicsNews.com and through other Aspen Core media publications. In this show, you'll hear both engineers and executives discuss news, challenges and opportunities for power electronics in markets such as automotive, industrial and consumer. Here is your host, Editor-in-Chief of PowerElectronicsNews.com and eeweb.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of PowerUp. Today we will talk about the challenges of integrating current sensors into wide-bandgap power converters. And we will analyze this topic with Ali Parsa Sirat and Babak Parkhideh from the Photovoltaic Integration Lab at the University of North Carolina at Charlotte. Integrating precise current sensing into wide-bandgap power converters faces challenges due to space constraints, high sensing speeds, and electromagnetic interference (EMI). Existing sensors struggle with size, speed, and EMI issues. So the podcast would explore the limitations and propose new methods to enhance sensor performance in wide-bandgap converters. So, let's talk with Ali and Babak. Hi Ali, hi Babak. Thanks a lot for coming on. How are you, Ali?
No problem. I'm pretty good.
And Babak, how are you? How is it going?
Good. Excited to be here.
Thank you everyone. So the topic of today is current sensor integration challenges in wide-bandgap power converters, wide-bandgap such as gallium nitride and silicon carbide. Before starting with a couple of questions that I have already prepared. So tell us more about you. Please introduce yourself, Ali, and then Babak.
Hello, everyone. My name is Ali Parsa Sirat. I am a former PhD student of Dr. Parkhideh at the University of North Carolina at Charlotte, with a concentration in power electronics and energy conversion systems. My research at UNC Charlotte focused on the hardware of power electronic system, specifically wide-bandgap based power converters operating at medium and high frequencies. And my research primarily focused on the identification of different types of feasible current sensing methods within this power converters, as well as their implementation and utilization methods. In my current position, I'm a senior power electronics engineer with East West Manufacturing, where I design and prototype high-frequency DC-DC and AC to DC converters for medium power industrial applications. So excited to be here.
Hello, everyone. I am Dr. Babak Parkhideh, an associate professor at the University of North Carolina at Charlotte. I specialized in power electronics and energy conversion systems, and at UNC Charlotte, I lead the Photovoltaic Integration Laboratory, where we focus on pioneer research in wide-bandgap power converters and advanced sensing technologies. Our work is dedicated to enhancing the performance and efficiency of next-generation power systems, aiming to meet the growing demands of renewable energy and high-power applications. Very excited to be here.
Thank you, Ali and Babak. So, Babak, let me start with you with the first question. So, wide-bandgap converters are known for their superior performance. So, could you elaborate on the unique characteristics of these converters and why they necessitate advanced current sensing techniques, as I mentioned at the start? So what role does precise current sensing play in ensuring their efficiency and reliability?
Well, wide-bandgap power converters operate at higher speeds and efficiencies compared to traditional silicon-based power converters. Devices can handle more current and voltage over a smaller area, making systems more compact and efficient. This capability is critical as it changes how we design not just the converters, but also associated components like magnetics, capacitors, and especially in this case, sensors. With WBG devices predominantly using MOSFET technology, unlike the IGBTs in silicon converters, in my view, it's essential to develop sensors that can match the new characteristics of these new advanced devices. Essentially, as our transistor evolve, so must our sensors. That's why I say new transistors need new sensors.
Thank you, Babak. So, Ali, talking instead of design trade-off challenges, so what are the key design trade-offs or challenges associated with choosing a single current sensing scheme for wide-bandgap converters?
Sure. Wide-bandgap power converters present several challenges and design trade-offs when choosing a current sensing scheme. Some of these challenges were present in conventional silicon-based converters, and they might have been compromised in one or more cases. However, wide-bandgap power converters with their higher switching speeds and smaller size make those type of compromises more difficult or even impossible in some cases. Invading the power circuit and isolation matters is a good place to begin. A good example is the use of a small shunt resistor that is placed in the low side of a lot of half-bridge legs to eliminate the need for isolation, while at the same time, it will provide an accurate and high-speed current measurement. However, this placement introduces a large parasitic inductance in many cases in the layout of, for example, a GaN half-bridge, which is not acceptable as an optimal layout for those type of converters. Other than that, the size of some current sensors can also be an important consideration. For example, current transformers or CDs have been used in a conventional converters for control and protection at AC nodes, like switching nodes in dual active bridge and LLC converters. But due to their magnetic core, some miniaturized wide bandgap based power converters may not be able to use them as they were using them in conventional silicon based power converters. As well as these issues, excessive EMI emissions within wide bandgap power converters can adversely affect the performance of some current sensors, processing circuits. And a good example could be Hall effect ICs or magnetoresistive sensors.
Thank you. Good. So, Babak, if we consider the various challenges, so how critical will be the development of accurate and adaptable current sensors for the broader adoption of wide bandgap technology? So, may you discuss the practical implications of integrating different types of current sensor into wide bandgap converters, especially concerning size, accuracy, and cost in particular?
I believe that the development of new current sensing schemes is really crucial for unlocking the full potential of WBG converters in new applications. For example, there is a significant potential for ultra compact isolated converters that require isolated current sensing with a bandwidth of DC all the way to 50 or even higher megahertz. These could be transformative, as you can imagine, for renewable energy systems and data centers. However, the absence of suitable sensors currently restricts these innovations to the R&D phase, preventing their broader applications. Moreover, for protection of WBG systems, the lack of dedicated current sensing products faces developers to create solutions in-house, which can be costly and time-consuming. By developing a dedicated line of adaptable, accurate, and cost-effective current sensors, we can support the development of WBG devices, not only in typical applications or conditions, but also under critical fault conditions, where they must handle currents many times their nominal rate. This advancement is essential for the broader adoption and reliability of WBG technology in various high-stakes environments.
So Ali, you and your team, of course, you did the analysis on current sensors for wide-bandgap power converters, as reported in your article. So one of them has been analyzed on powerelectronicsnews.com. So what novel method or improvements do you foresee in enhancing the performance of current sensor in wide-bandgap converters?
It is clear from the points that Babak and I raised earlier that a number of non-invasive and cost-effective current sensors on the market lack some key characteristics that are associated with wide-bandgap-based converters. Specifically, by developing on-chip or directly attaching current sensors, parasitic effects can be minimized and accuracy can be improved. A good example can be an on-chip flux gate sensor, or we may call it micro flux gate, as it is capable of reading currents in either a common or differential manner with a high level of accuracy and noise immunity. It was a good example. You may find a similar part that Texas Instrument introduced a few years ago. Also, when referring to non-invasive current sensors, only inductive-based current sensors like CTs and Rogowski coils can achieve a high sensing bandwidth. Ultra-high frequency inductive sensors can be integrated into wide-bandgap power converters via technologies such as MEMS, nanocrystalline materials, and PCB integration of coils aligned with the innovation in electronics processing circuit. However, inductive current sensors cannot sense DC current. An alternative method for overcoming this problem may be to use the hybrid current sensing scheme. And clearly, for a good example, an on-chip or PCB embedded coil could be combined with an on-chip DC sensor such as on-chip flux gate or micro flux gate that I was mentioning earlier, to make sure that we're gonna have a good bandwidth starting from DC up to very high frequency to read the current with a good accuracy and a good noise immunity while we maintaining a super small size.
Thank you, Ali. So in conclusion, guys, so Ali and then Babak, so my last one, what are your thoughts on the future prospects of current sensor technology alongside the continued advancement in terms of wide-bandgap power conversion systems? Ali and then Babak.
So as wide-bandgap power conversion systems continue to evolve, the future prospects of current sensor technology are both promising and challenging. Other than the challenges that I mentioned earlier, promising aspects can be in integration and miniaturization of current sensors technology, also higher working frequency and much higher bandwidth, sensing bandwidth, also advanced materials and physical innovations, along with machine learning and AI-powered processing. In a nutshell, the future of current sensor technology lies in innovation, interdisciplinary collaboration, and addressing the mentioned challenges. As wide-bandgap power conversion systems become more prevalent, sensor advancement will play a pivotal role in achieving efficient, reliable, and sustainable energy systems. Thank you.
So, as a researcher in this field, I think in addition to incremental improvements in electrical characteristics of current sensors that we discussed, I am particularly excited about the potential to develop three-dimensional sensing capabilities for current sensors, as we've seen for other sensors. Currently, nearly all commercial products rely on one-dimensional sensing. Expanding this to multiple dimensions could significantly enhance the flexibility and effectiveness of not only the current sensors, but also the system they support. For instance, consider the impact of a cost-effective, compact 1,000 amp solid-state circuit breaker designed for fast charging stations and cars, or non-invasive 50 megahertz current sensors that could derive much higher density converters crucial for powering advanced AI technologies and photovoltaic or energy storage industry. And in that manner, our research team, along with our partners, is committed to unlocking these innovation solutions. And we are aiming to revolutionize, hopefully, the next generation of electrification technologies.
Thank you. We are in conclusion. Thanks a lot, Ali and Babak, for your time and for the participation at the PowerUP podcast. It has been a wonderful conversation, and stay tuned. Thank you, everyone.
That brings us to the end of this episode. Stay tuned with more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.